CPUFreq is one of the most important power management features that Xen RM doesn't have so far, unlike Xen on x86. So, before digging into the CPUFreq internals, I would like to introduce myself, my team. So, we are a team of developers based in Kyiv, Ukraine. We are focusing on many topics: Xenon ARM, Renaissance Generation 3, board support and maintenance, Xen real-time power management, OptiE, Android hardware abstraction layers. What is more, we are members of Azure Engineering and pushing for Xen usage there. Also, we are developing a Yocto-based build system for multi-domain distribution. Also, we upstream all our work to Xen project, to Linux kernel. You can see us at GitHub. So today I will cover next topic. So I will speak about why the CPUFreq is needed, why it is so important, why Xen needs to be involved in CPUFreq. I will speak about the current status. Then I look through the possible approach for the CPUFreq in Xen. So after that I will speak about the CPUFreq PoC based on the approach I have chosen. After that, I will show you the numbers so you will be able to see the real benefit of the CPUFreq. After that, I will speak about the improvement which was proposed in Xen manifest. So, I believe that all of you know what the CPUFreq is intended for. Yes, it is a power management feature for controlling CPU frequency on the fly, depending on the actual needs, taking into account CPU utilization, CPU load. So, what benefit is expected from the CPUFreq? Xen becomes more popular in embedded world this day, and the demand for the CPUFreq comes from this world, where the ARM platform are widely used. So, there are two orthogonal things that CPUFreq can help with: performance and power savings. Power savings. For battery-powered devices, automotive, embedded, mobile, whatever, it doesn't make any sense to write around CPU at high frequency when not needed. These devices must be as power efficient as possible in order to preserve installed battery. So also running CPU at high frequency all the time may heat up CPU, reducing its life. So on the other side, when we deal with heavy use cases, we want to get appropriate benefit from the system. We want to get appropriate performance. And CPUFreq allows to benefit from the CPU turbo frequencies if board supports them. So without Xen, it is not possible. We can't just set high frequency from the bootloader and let the CPU to run at such high frequency all the time. So there must be some entity in the system to scale the frequency down from time to time, as this entity is a CPUFreq. So why Xen needs to be involved in CPUFreq? So why don't just pursue CPUFreq stuff to, let's say, domain 0 or hardware domain, and let things work as they work on parent system without Xen? So why Xen needs to be involved? The answer here is the CPU virtualization is done by hypervisor, and the abstract OS doesn't know anything about the PCPUs because it runs on vCPUs only. So it's quite clear that we can't create working solution without modifying Xen at all. It's only the Xen single system component who has all required information. So, current status. As I said above, Xen on x86 has CPUFreq out of the box, but RM support is missing so far. So there are two possible modes, domain 0 based CPUFreq and hypervisor based CPUFreq. So these modes differ in where the CPU logic is implemented. So the hypervisor by the CPUFreq is more appropriate to be used in ARM embedded platforms because domain zero by the CPUFreq implies hard with CPU pinning and having CPUFreq infrastructure in the domain zero. But this requirement may conflict with requirement of thin domain zero or non-Linux domain zero. So hypervisor by the CPUFreq. So as you can see, the CPUFreq infrastructure in CN is similar to Linux. So two scaling drivers for x86 are supported. So although it is a hypervisor by the CPUFreq, it is requires domain zero to be involved, but not to scale to CPU, just to parse SCP tables and upload information to Xen, and controlling CPUFreq parameters in runtime via Xen tool. So the ARM support is missing so far. It was to mention that there was an attempt from Oleksandr Tyshchenko from GlobalLogic to create support from ARM, which included an activity for making SPI-specific CPUFreq stuff more generic. I will consider this approach down the presentation. So, possible approaches of CPUFreq ARM. So, before digging into the possible approaches, I would like to draw your attention to the one problem, which is the frequency changing interface. So CPUFreq just make a decision and issues platform-dependent call which contains frequency the CPU should run with. But the possible question, who should actually scale the CPU? Xen or hardware domain offer dedicated AP controllers, some power management coprocessor. So the list of required for DVFS components are quite big. You can see modern Linux implementations, so how many components are involved in DVFS. Core, regulator framework, terminal framework, platform drivers, so and the possible approaches we are about to consider differ exactly in frequency change interface. So, Xen plus Havedon solution. Hardware domain scales to CPU. Oleksandr Tyshchenko from GlobalLogic proposed a split model where front-end driver in Xen interacts with back-end driver in hardware domain in order to scale the CPUs. But this solution hasn't been accepted by Xen community yet, and status this work, I would say, is freeze. So pros of this approach. The main beauty of this approach is that we don't need to port a lot of things to Xen. So this solution is going to be generic. Cons. The way how the Linux backend driver implemented won't be acceptable by Linux community, so design is definitely needed. So complex communication interface between Xen and hardware domain. syscalls, header calls, custom device key bindings, etc. It is a not completely safe solution. Letting guest OS or even hardware domain manage device power management is one thing, but letting it manage CPU is a big risk. Second, own Xen solution. Xen scales the CPU. So, quite clear that we need to port all the DVFS related stuff for the CPUFreq scaling drivers in Xen to be able to actually realize certain OPP, operation performance point, which is a pair, voltage, and frequency. So, pros. It is a not generic but safe and more architecturally cleaner solution than previous one. Having all in Xen, we don't depend neither on potentially malicious guest domain nor on driver bucket running. Cons. We are going to end up having a lot of code in Xen. since we will have to keep as many scaling drivers in CERN, as many platforms we want to support. So another enormous development effort is needed to get this support in and maintain it, since the list of required components is quite big. CERN plus SCP solution. So it is yet another approach based on the popular at the moment ARM SCMI protocol. So ARM SCMI, System Control Manager, System Control and Management Interface protocol follows the recent trend in the industry to provide an embedded microcontroller to abstract power and other system tasks. So the SCMI protocol is used between this embedded microcontroller, which is the SCP in terms of protocol, and the application processors. Usually, CP provides a lot of services, and one of the services is the performance management, which includes DVFS for CPU core cluster, what we actually need for the CPUFreq. So the protocol specification is officially published, so, and SCMI related drivers upstream to Linux kernel. So SCP scales PCPUs. So the generic idea of this approach is that there is some firmware which, being a server, runs on dedicated IP core provided SCMI services. On other side, there is a scaling driver in CERN, which being a client consumes these services. So the CPUFreq scaling driver is in CERN just signals a PP change request directly to the CP. That's all. So requirement. It was to say that some mailbox IP needed for IPC between SCP and Xen. Also, the main point that some corresponding firmware must be present, which provides SCMI services. This is the main requirement. So, but what to do if the dedicated IP core is absent on target platform or performs other than power management tasks? So what to do? Is it a blocker for us or not? No, the lack of dedicated IP core isn't a blocker. So Andrei Przevar SMC-triggered mailbox approach with his PoC code for all winners demonstrates that. So the generic idea of this approach is to teach firmware which runs on the very same application cores as CERN runs, but in the L3 exception level to perform SCP functionality and provides SCMI services, and use secure monitor calls for communication. Such solution is going to be a good compromise for the ARM platforms which don't have a dedicated IP core for being SCP, but have firmware running in trusted software layer. This is actually ARM trusted firmware. So the SMC triggered mailbox driver emulates mailbox which signals transmitted data via SMC instruction. So the mailbox receiver is implemented in firmware and returns data when it returns execution to the non-secure world again. So this is a completely synchronous case. So pros of this approach. I think it is a secure and architecturally clear solution. So there is no reason not to trust firmware running in trusted software layer, or not to trust firmware running on dedicated embedded controller in SoC. So it is going to be a generic solution, since the only mailbox driver is going to be one platform-dependent component. So easy to implement this approach comparing to the previous one. Once the common part was implemented, it would be too easy add support for new board. So what we need to add to support new platform is a simple mailbox driver to implement a minimum set of functions. That's all. So no complex communication interface, just SCMI protocol. And the last one, only this approach allows to have guest inputs in CN with minimal modification in code. So, cons. So the main cons is that firmware. So the corresponding firmware which provides SCMI services must be present. It is a main requirement. So it can be either firmware running in EL3 exception level or run on dedicated IP core, but it must be present. So next cons is seems CPI related only, but so for the if we use a CPI protocol, a CPI is also ARM protocol, system control and power interface. I would say it is an early version of SCMI protocol. It is generic ARM and also officially published, also upstreamed, but it is, let's say, early version of SCMI protocol. And for this CPI protocol, probably we need to emulate all SCPI requests in CN for the CN to be an SCP for guest. So, as you may understand, I have already chosen CN plus SCP solution. I think that this solution is more appropriate across all proposed solutions. So, CN plus SCP our choice. So, CPUFreq PoC. So, main points. ARM SCPI. So, I built this PoC on top of ARM SCPI. Why didn't use ARM SCMI? So when I was doing research, the SCMI Linux support was missed. And next, the range of capabilities the SCPI has was enough to implement this PoC. But we will probably move to the SCMI, so or CN could support both protocols. It is discussable. So, next, SMC triggered mailbox. So I borrowed the idea of SMC triggered mailbox driver which emulates mailbox which signals transmitted data via SMC call. So the reason was in the lack of dedicated IP core on platform I worked with. And this idea looked reasonable to me. So modified firmware. It was feasible to me to modify untrusted firmware, since the official BSP release I used provided both firmware and software. So in classic embedded scenario, it is going to be feasible as well, where the same entity provided both firmware and software. So just a few seconds. Just a few sentences about what we have if we run vendors BSP with CN and without CN. So without CN. So the CPUFreq feature works out of the box if we run Linux from vendors BSP. So the BSP release for R-Car Gen3 boards comes with CPUFreq enabled in Linux. It uses DT CPUFreq, this device to basic CPUFreq. So the DVFS related properties are described in the device tree and driver extracts this information. So you can see the example of real CPU node. So, but if we run that Linux from BSP as a domain 0 or as hardware domain, we get CPUFreq feature broken. It is expected actually, so there is no issue. Since when CN creates device tree for guests, it inserts only dummy CPU nodes and all DVFS related properties which the original node has are not passed to the guest device 3. So this is the example of guest with CPU node. So there is no clock supply, no OPT, no clock properties. So we get CPUFreq feature broken. Okay, so I will skip the POC implementation details, unfortunately. A lot of time needed to describe all of them, but the corresponding presentation slides are present, so you will be able to read them after. So this slide demonstrates what I had from the beginning. So this slide demonstrates what I got in the end. So proposed CEN plus SCP solution is not limited by only using ARM trusted firmware for provided services. So if the ARM platform you're working with already has a dedicated IP core providing services, then even better. So the only one thing you need to add to support in CEN to benefit from the CPUFreq enabled CEN is to a simple mailbox driver. So focus on your mailbox driver only. So the important note here is that the CEN tool stack wasn't modified. So in order to minimize changes in the common code and to retain current interface, the SCPI-based CPUFreq was implemented in a way to be absolutely okay with SCPI performance states. So the CEN PM tool works out of the box on RM. So status. This POC works, it is stable enough, no random freezes, crashes. It is possible to control CPUFreq parameters in runtime. So I have already sent RFC patch series to the CEN mailing list which initially implements this solution. So the patch series looks quite huge from the first glance. It pulls a lot of third-party code from Linux, but I believe that the number of lines of code it adds can be significantly reduced. So there is definitely a way for optimization. So as example, you can see the CEN boot log and output of the CEN PM command. So benchmarking results. It is a quite interesting paragraph. So the target hardware is a Renaissance server board with R-Car Gen3 S3 SoC. It is a quite powerful SoC. 4 Cortex A57 cores, 4 Cortex A53 cores, Cortex R7 core, so target software. I decided to use our demo system which was shown at last CES. So it is a virtualized system based powered by CEN hypervisor and consists of 4 domains. In domain 0, there is no hardware drivers at all, generic ARM v8 Linux. Cluster domain, which is a automotive grade Linux based on Renaissance BSP. IVI domain, which is a Android Auto. And a cloud services domain, which is a generic ARM VM Linux. And this all on top of them with CPUFreq patches I did in the context of this POC. So what to measure? So I did a power consumption measurement for A57 cluster only. So I measured power consumption in 2 modes. with DVFS and without DVFS. With DVFS, so the CPUFreq settings is on-demand governor, so the frequency is changed in runtime. So the 5 OPPs, last 2 OPPs are turbo OPPs, and the turbo mode enabled for the CPUFreq to be able to set any frequencies in runtime. And without DVFS. Without DVFS, it is a retrospective governor and single OPP, OPP nominal, 1.5 gigahertz. So this is actually equivalent to Xen without CPUFreq. So this frequency is set from a bootloader, and if we don't have the CPUFreq, this frequency is constant during the whole cycle. So use cases. As you can see, most of the use cases are typical for Android. Audio playback, video playback, navigation, and etc. So how to measure? This slide describes actually what I measure and how I calculated power consumption. So I use, for example, flag multimeter with average option, such a convenient tool, I would say. So power consumption, so you can see this is a table, so you can see the benefit. We have benefit for the first 5 use cases. So this is the real benefit, and the Android playback. But so I have 2 Android. I have 2 audio playbacks. One audio playback in Android, next audio playback in Azure Linux. So this playback is the winner. So you can see benefit more than 30%. So this is benefit why? Because low OPP are used during these use cases. So, but with navigation, we have a drawback. Drawback because high OPP are used. It is a heavy use case. So next, boot time. So boot time it is quite important things. So nobody wants, for example, nobody wants to wait for a long time. Why the device, smartphone and laptop is booted. So I measured boot time, and so I compare it with turbo frequency and without on nominal frequency. So as you can see, there is a benefit about 8%. So comparing to the nominal frequency. H3 SoC has highest OPP, highest turbo frequency 1.7 GHz, but M3 SoC has 1.8 GHz. So I expect more benefit on M3 SoC. So I expect it would be more than 8%. So improvement, yes, input. So this improvement was proposed in Xen mailing list. So it is supposed to affect not only a CPI-based or a semi-based CPUFreq, but the whole system. So currently the decision about the frequency change is made by Xen exclusively, but Xen scheduling the CPU doesn't know much about the guest internals. All Xen sees is wait for interrupts, traps, hyperpolls, but guest can track the actual utilization of the CPU, but Xen doesn't see such granular information. So therefore, Xen needs additional input from guest to make a proper decision on the frequencies the CPU should run with. So the idea is that guest could provide some input to Xen, for example, by signaling OPP change request up to Xen, and Xen then pick this request up and act upon them. So probably we would need some combined approach. So this also was proposed by Xen community guys. So first, tell Xen about the power management strategies for use for certain guests. So different guests can be treated differently. RT guest, real-time guest in one way, non-real-time guest in another way, entertainment guest in third way. So second, allow some guests based on policy, of course, to signal OPP change request to Xen. Xen takes this into account, but it may decide to not act immediately because it is going to schedule another CPU, for example. So, and third, have some way for actually realizing certain OPP. Maybe via SCMI or a CPI client like this PoC does, or in another way. So, two possible options with guest input. Just continue of previous idea. So first, Xen doesn't have CPUFreq logic at all. So Xen doesn't measure the CPU utilization. So then it collects OPP change request from guest. After that, it makes a decision based on this request and some policy. And as finished, it signals final OPP change request to the SCP. Second option, Xen has CPUFreq logic. It measures CPU utilization, like right now. In addition, it can collect the guest change request. After that, it makes decision based on both its viewpoint and guest request. After that, it sends final OPP change request to SCP. I think that the first option is more clear and more simple, but anyway, it is discussable. So we have two possible modes. So I think it's worth to make a simple PoC to POC to try it out and to see the real benefit from the both. So it is discussable. So interesting thing was proposed by Andrei Prajvara is how guest will signal OPP change request to Xen. So how? Extra PV virtualization protocol needed or not needed. So SMC triggered mailbox solution. So use SMC mailbox for providing virtual CPI or SCMI services to guests. So mailbox building allows using HVC for triggering the services, and Xen could pick this request up and act upon them. So how it is supposed to work? Xen creates virtual CPI DT nodes for guests and use SMC mailbox with HVC method. So after that, HVC handlers in Xen redirect this OPP change request to CPUFreq PoC. This is simple. Goals. Goals are obvious. No extra PV protocol. Platform agnostic for guests. So while making all guest requests ending up in Xen. Simple and clear flow. So this picture demonstrates how it would look like. So this is the links. So you can see patches for Xen and for the firmware I modified. So this is the link. This is my email. You can email me regarding any questions. So, thank you. Questions?
I would suggest to take the question outside after, because the other group started 15 minutes ago. So we are quite late compared to the other talk.
We got out the sync.
Yeah.
Great work.
Thank you. Any other question?
Hello. I would like to ask that your associates support per CPUFreq or based on cluster CPUFreq. Because some associates do not support CPUFreq chains based on per CPU. This is the only freq based on cluster.
Okay, so I understand the question. So, as for R-Car Gen3 board, different frequency on each core are not allowed. So all cores inside the cluster share the clock and the voltage. This is as for SoC. But coding itself allows to deal with different clusters and different clocks on each core. So this CPUFreq PoC was written in a way to be able to deal with if different frequencies you used on different cores.
Thank you. So have you included the symbol in your CPUFreq? Symbol, temperature. Temperature.
It would be better to leave temperature to the firmware, because if firmware measure temperature, for example, and if the temperature limit is running out, it just not set high OPP or use a secure interrupt to trigger when temperature reaches the threshold and firmware to scale down the frequency. So I'm not sure it is a good idea to put temperature to 10. So this is personally my opinion.
Can I stop you guys? Otherwise the time is getting off your colleague. We have enough.